So yeah, the title, trying to be a little bit evocative, really trying to provide an overview of the reasons, or an insight into some of the reasons for the success in Germany, in the Bavaria region, and to see if some of these ingredients for success actually can play a role in other regions and can be taken away. So, as mentioned, my name is Neil Farquharson. I work for ERDWERK. We're based in Munich. I've been with ERDWERK since about 2014, as mentioned, as a project manager, senior project manager, for guiding the deep geothermal projects through the whole process. So in my presentation, I will provide a brief overview of the development within Bavaria, then, as mentioned, trying to pick out some of the reasons for success, and then start to look to the future, or start to look where this success has brought us. Where are we today, and where will that take us in the future? And then, as mentioned, if there is really a template or some takeaways from the experience that we have for other regions, for other cities. So maybe briefly regarding ERDWERK, for the people who don't know of us, we're a German consultancy. We're based in Munich. We were founded in 2002 by Dr. Achim Schubert, who we unfortunately lost tragically last year to a heart attack. So yeah, difficult year for everyone involved with the company, but we have a really strong team of over 30 geoscientists and drilling engineers and production engineers, and he instilled a lot of his spirit in us, and we would want to continue driving that forward. So Dr. Achim Schubert, he was a hydrogeologist. So the company was founded on real hydrogeological principles. However, since founding in 2002, the company's developed, and now we look to offer the complete service packages for all the subsurface works, meaning that we have the capabilities, the expertise through geological reservoir engineering, targeting, drilling engineering, well planning, well testing, production engineering, bringing that all together within the project management. So really trying to offer all the services out of one hand. So we like to see ourselves as a leading consultant for deep geothermal projects within Europe. We only do geothermal projects, and about 80–90% of our work is deep geothermal, with some surface, near surface geothermal projects as well. Currently, we have projects all over Europe. So Germany, obviously, recently in Belgium, currently in Switzerland, Finland, UK. Further afield, we've done some capacity building work in Africa, and we're currently very active in Central and South America with some smaller projects. We're hopefully building on that. We're quite a young, dynamic team, and we firmly believe that geological understanding for projects is a good basis, but that it needs to go beyond that, integrating all disciplines together, that geologists are working with drilling engineers, that they're sitting together, that they understand the respective disciplines very well to be able to provide a very comprehensive management and technical management of the projects. Geothermal projects, from our perspective, require very good planning. It's not an oil and gas field where we have 20+ wells or a portfolio of wells. It's 2 wells if it's a hydrothermal project, and you only have this chance to get it right. So we put a real emphasis on planning for our projects, so it's planned correctly and able to be as successful as possible. So looking a bit at the geothermal, also the energy market in Germany. It's a pretty typical build for pretty typical picture for the whole of Europe. Renewables playing a relatively minor role in the entire energy mix, and geothermal being a very small proportion of that. So a niche within a niche. So yeah, so it's something which we're seeing. The geothermal market is developing slowly. It has its boom times in the past, which we'll talk about, but there seems to be a new wave at the moment. a lot of new interest in the geothermal sector. So we're hoping that maybe in a year or two that this picture will be a little bit more different. So Bavaria itself, so in the southeast of Germany, plays a significant role in the number of geothermal projects. So 14 of the 26 operating heat and power geothermal projects in Germany can be found in Bavaria. So over 50% of the projects are found there. However, the future role of the Rheingraben, so in the kind of west of Germany and North Germany, shouldn't be understated, and they will really be, I think, in the next few years, developing to a scale that we see now in Bavaria. So on the left-hand side of this slide, we have an image taken from a LEAG report from 2018 showing the hydrothermal potential for 20 degrees. And as we see, it is quite well distributed across Germany. There's lots of regions where theoretically a hydrothermal project would produce a temperature of 20 degrees Celsius. But as we go through these slides here, or through the different pictures, as the temperature increases 40 degrees, 60 degrees, we see that the regions where that's theoretically possible starts to get smaller and smaller. And as we reach then maybe 100 degrees Celsius, where it's probably more interesting for a lot of projects, we see that the regions where that's theoretically possible start to get very, very limited. So we have in the southeast, we have then the well-developed region around Munich and in Bavaria, and in the west we can see Rheingraben region, and in the North German basin. So there's quite a lot going on in this graphic here, but it's a nice overview of the timeline for the evolution of drilling within Bavaria. So going from 1990 to 2020 across the top. On the x-axis, and the y is just summing up the number of meters drilled. So it really gives an indication of how active the drilling market was within the region for geothermal projects. In the yellow boxes, we have the number of projects being drilled per year. So I guess it's important to understand that the geothermal heat in Bavaria is nothing new. There was a lot of oil and gas exploration around the sort of the 1930s, 1940s, and a number of those wells discovered hot water instead of hydrocarbons, specifically Bad Fussing, which is on the east side of Bavaria near to the Austrian border. Famously, that region became a thermal bath, but there wasn't really any considerations at the time to use that heat energy as a real resource, other than for I guess for leisure or for any kind of medical reasons. Through the 60s, 70s, 80s, then the hydrocarbons were explored further, and there's quite an extensive number of hydrocarbon wells which were drilled across the region, and they form the basis for the understanding of the deep geology across the region. So the fall in oil price around the 1990s was probably one of the first kickstarters for people involved in the deep exploration to start to think towards geothermal and whether it's a feasible resource for supplying heat. One of the first well-known and successful projects coming online in about 2002 then was ERDWERK, which is in the northeast side of Munich, and there's a very famous thermal baths there, but also a district heating network which is supplied with heat from the wells. So in 2003, there was quite an important report, the TAB report, which really demonstrated or looked to demonstrate the theoretical potential for producing electricity from the geothermal resources in Germany. So this report quite boldly stated that there was real potential to produce electricity, and that to reach what was really required is 350 plants each with a capacity of 10 megawatts electric could be developed. We know today that we're nowhere near that. Maybe less than 5% of that has been achieved. But it was really an eye-opener at this point in time to a lot of people who maybe didn't consider the geothermal resources within Germany as a viable option for a project. So this was one of the first Kickstarters, and then coming shortly after, in 2004, was the Bavarian Geothermal Atlas. So this was one of the first reports of its kind, just providing really the first indications of where are the regions with the most potential. And we can see in the plot then that it's maybe slightly skewed because in 2008 we had. Probably more due to coincidence, a lot of projects being drilled concurrently, but it really meant that in the background from 2003, 2004 onwards, quite a number of projects were being planned and came on board. So all of those projects being planned maybe at the same time from different operators, different developers, as mentioned, coincidentally, then all happening around this 2007, 2008 period. It was quite a boom at that time. After that, we did have some implications of the financial crisis coming in 2008. And also maybe the market was a little bit saturated immediately, that existing projects needed a bit more time to see how it all operated, how successful it really was before they could expand or before neighboring projects will come on board. So there we saw then a pretty immediate drop-off in the following years. 2013, 14, 15, very quiet within the region. But slowly, as either existing projects look to develop, or as we'll talk about later on in this presentation, the city of Munich, the utilities company ERDWERK in München, made a commitment to use geothermal, to utilize geothermal heat for the district heating networks. We start to see that the trend changes a little bit, or improves a little bit. So looking at a bit spatially, I think it's interesting to see in 2002 the number of claims which were active or secured within the region. So on the left-hand side, 2002, so the gray is the city of Munich. And we have 4 projects, 4 claims. These are really the pioneer projects for the time, and yeah, some of the most successful projects in the region. Without them, maybe we wouldn't have had the progress we've had today. The boom times came then on the right, 2007. We can see the number of claims which have been submitted, secured in red, and in black, the claims which are actually producing, whether it's heat for district heating or electricity or thermal baths. We can also see, it's interesting to note that the claims go quite far, so left to the west, towards the West Bavarian border with Baden-Württemberg. This region hasn't really demonstrated any further development today because of the unsuccessful projects, Weilheim, for example, which maybe slowed up the progress a little bit. And it also demonstrates that there's a lot of unknowns regarding the deep geology in those regions. We can also see a gap east of Munich, and this gap represents a known thermal anomaly. That's a cooler region where the temperatures aren't so suitable for district heating projects or electricity producing projects. The cold anomaly is known to be an influence from the Alps, which are lying to the south, due to cooler water infiltrating the formations coming down from the Alps. So there's a lot going on in this map, but this is really a snapshot of today, well, end of 2019. So there's a few updates which have happened to this map, but we can see quite clearly, again, orange being not producing claims and black being producing claims. We can see that there are a lot of projects which have come on board. And also in the east, on the Bavarian Austrian border, we also have one of the really upcoming regions at the moment where we've seen probably the most development of new projects in the last few years. So Kirchweida, maybe it's a little bit older, it's 10 years old or so now, but the project which has recently come online, not in this map, in Bruck, Rupertiwinkel in the bottom right corner, which is currently being developed. There's a lot of interest in this region because the conditions are very good. So the geological conditions are very good, the potential is very good, and the temperatures are higher. So there's a lot of combined heat and power projects, which are obviously very attractive for investors. We'll address the geology very briefly, I guess, in the coming slides, but I think it's good just to have a look at this map and just to kind of point out the distribution of what kind of projects we have. So to the north of Munich, where the temperatures are slightly cooler, so between 70 and 80 degrees Celsius, at a depth of about 2,000 meters. All the projects are exclusively heat projects. The majority of the projects are for local communities, Unter Schleißheim, Gerching, Ismaning, Aschheim, Poing, Erding there in the top right. They're all 2 to 4 wells. 4 wells we have here in Unterföhring, producing 4 district heating networks. To the south of Munich, there is maybe the sweet spot where the temperatures are a bit higher, and then we have here a number of combined heat and power projects. Sauerlach, a very famous heat and power project, producing 5 megawatts electric and about 4 megawatts thermal, and also the neighboring Kirchstockach and Dunha. The southernmost project here, or successful project, being Holzkirchen, a very deep project, over 5,000 vertical meters depth, of the 2 wells, producing well over 150 degrees Celsius. Was at the point, when it was completed a couple of years ago, was one of the deepest hydrogeothermal projects in the world. So the southernmost projects are known to be more technically challenging. I think with the depth, there gets a lot of problems with instability. So it's quite a technical challenge. So as I mentioned, we want to really try and pick out some of the reasons for success for the Bavarian region. They're summarized here, trying to kind of weight them a little bit on their importance. So in terms of the size of the circle. So we're going to go into each one of these in a little bit more detail, starting with the favorable geology, the well-known favorable geology of the region. So within the Molasse Basin in the southeast of Germany, famously lying beneath Munich, we have the Malm Reservoir. So this is a carbonate reservoir of Upper Jurassic age. It gets deeper from north to south, so it's dipping from north to south towards the Alp, where it dips under the Alps. And as with the geothermal gradient and with depth, the temperature increases. So in Munich, as mentioned, maybe north of Munich, 7 to 80 degrees, and then to Munich in the south, there may be going up over 100, 120 degrees. And as mentioned, in the far south, where Holzkirchen, the project Holzkirchen is, we're at around 150 degrees Celsius. One of the most positive things about this reservoir is the water chemistry. So sometime in the past, so it's Jurassic age, so it's millions and millions and millions, hundreds of millions of years old, but sometime in its lifespan, the theory is that the formation water was exchanged, meaning that the fluids which are in the reservoir now reservoir now have a very, very nice water chemistry. The dissolved minerals is very low, salinity is quite low, meaning operational problems, scaling is an issue, but corrosion really isn't a significant issue within the wells within the region. And this also means during testing that in a lot of cases, the test water can actually be filtered and then be disposed of in the normal drainage system of a region. So the permeability is also very, very good. So it means we're getting flow rates of anywhere between 50 and 100 liters a second. So within the formation, within the Malm reservoir itself, there are a number of different characteristics which mean it's very productive. It's dominated by karst. So there's a lot of very large voids, washed out karstic formations. There is intergranular porosity and also significant faulting and fracturing. So the knowledge really, I think the geology can be spoken about for hours. There are many, many papers, a lot of research, a lot of time has been invested into understanding this formation. But simply being a carbonate, it was deposited as reefs, meaning that we have reefs and banks, and the reefs being the targets because they demonstrate the higher porosity, and the banks where the formations tends to be a little bit more highly compacted are generally then avoided. The question is then, is the Malm, is this kind of formation unique? Are there any similar reservoirs worldwide? Yes, there probably are quite a few different examples. Closer to home, we can consider the carbonate platforms which extend across the Netherlands. You see here, well, probably not quite so easily, but we have the outline of France, Belgium, and the Netherlands. Great Britain is obviously there, and the blue fill, the blue block fill, we have the carbonate platforms extending across. So yeah, maybe it's interesting just to do a bit of comparison. So we have here in the table the Malm reservoir, and then against it the Dinantian, so this carbonate platform which you saw in the previous slide, extending across Belgium, the Netherlands, and into the UK. And there are some similarities. The age is obviously different. I mean, 150 million years difference is quite a significant time, but the depositional environment, so the environment which the formations were created, have some similarities. Tropical, warm, epicontinental, shallow marine environments, meaning that, yeah, carbonates with limestones, dolomites, and marls. Yeah, well, the diagenesis is something very geological and beyond the scope of this presentation, but there is a relationship between the porosity and the dolomitization. So there are some question marks regarding Dinantian and how much the dolomitization has taken place. But as mentioned, the depositional environment is very similar as a foreland basin. The differences do occur when comparing these two formations. The low salinity, almost fresh water, which we experience in the Malm, is not the case in the Dinantian, and that's one of the biggest challenges for deep geothermal projects in the Netherlands and Belgium, and potentially the UK, is dealing with that quite corrosive, sometimes naturally occurring radioactive fluids. So dealing with it during testing and during drilling, but also over the 20, hopefully 30-year lifespan of a project to ensure that it's not causing any long-term effects in the well. So geothermal gradient is obviously quite similar, and the porosity, I think shallow porosity in the both formations is dominated by a lot of karst. There's similarities there, but at depth this starts to get a little bit more unclear. So the Dinantian at high depth is potentially more fracture dominated porosity, as opposed to finding karst at that kind of depth. So economic viability is obviously key to pretty much all projects. They need to be economically attractive for investors, or economically viable for the operator. But what we do know, obviously, is there is a heat demand. That 50% of the energy demand in a household is heating or cooling, and we know that a good operating geothermal project, hydrogeothermal project, producing 70, 80, 90, 100 degrees, can provide the heat required. It's always good to include some real world numbers where possible. So in terms of cost, so I took these numbers from the project from Pullach on the southwest of Munich. A very successful project, one of the first projects in the region. And we can see here quite simply that the first two wells costing just shy of 11 million, the third well costing about 7 million. So 3 wells, they've invested there 18 million euros in total. The energy center, so the heat exchangers, costing then just shy of 4 million, and then the district heating networks in 2 parts, which is always interesting to see, because the cost implications of the district heating network are obviously very significant compared to the drilling of the wells. So if the district heating network is already within a community and they just need to drill the wells and then tap into the district heating network, then it starts to become very attractive. So the total investment, including operating costs, expected up to 2054 for the Pullach project, is around 76 million euros. So I thought it might be interesting just to have a look at the capex opex cost and the rate and the return of investment over time on a bit of a theoretical generalized scale, but we can have a look at the difference between maybe heat and power projects here. So taking the first example of a heat project, the investment required. So we have years across the X and euros or million euros in the Y, and we have different phases. We have the planning phase, drilling phase, development of any heat or power station, grid, so district heating network development, and then beyond that is just operating. And we know from a heat project that we invest a little bit of money in the planning, and then a good chunk, 10, 15 million in the drilling. And then we have the heat exchangers, which is a little bit more of an investment. And then we have the 30, 40 million investment maybe for the district heating network. So after that period and a lot of investment, we go into the operating phase with no further real investment, and there the investment costs level off a little bit. That means the return of investment for a heat project does take a long time, but it's a stable return of investment. So we obviously go into the minus here as we're investing, but assuming that the grid development is in phases, at a particular point, the heat can be started to be sold to customers, and you see the return of investment over that period of time. Comparing that to power, the planning, the drilling has some similarities then. Maybe slightly more expensive to construct the power station, but beyond that, you start earning. There's no more significant investments. There's no, if it's just a pure power project, there's no grid to be built. You can just start delivering electricity into the electrical grid, which means the return of investment is obviously significantly quicker and more due to feed-in tariffs as well. So the investment in the project itself is a little bit less potentially without the district heating network, and then we're seeing then almost from the first day that the power station is online, you're starting to generate income. So we know for a heat project, that the cost for a heat project needs to be somewhere between 25 and 35 euros per thermal megawatt, assuming that the customer will purchase that heat for between 75 and 80 euros per megawatt. So the political framework is obviously, maybe one of the most difficult things to influence. Within Germany, there's a number of different credit systems to provide low interest loans with some grants. They can be taken from different suppliers, but nationally, the KfW offers a series of different options. But taking an example of maybe a 2,000 meter deep 2-well project, they can expect to get somewhere between 2.5, 3 million euros in low interest credit and grants to support the project. Sometimes regionally, for example, within Bavaria, there's other supporting banks, development banks, who also offer very low interest rates credit for different projects. However, there's no expiration insurance. Other countries, the Netherlands, for example, Belgium as well, also Switzerland, do have some kind of mechanism for protecting the project developer should they have an unsuccessful well. That isn't the case. There is no state expiration insurance within Germany, and there never was. There were some private solutions. However, they fell away really around 2013 due to a couple of unsuccessful projects. However, with recent developments and some very successful projects over the years, there are a few more options which are coming back onto the market. So it could be a development for the next few years. So public acceptance. It's known within Germany that there's a high acceptance for green projects. So there is definitely a desire for different green energy projects to come on board. We know within the Bavaria region that we were, I guess, lucky or fortunate that the first few projects were very successful, and the subsequent projects as well. So the number of unsuccessful projects has been really very, very minimum. You can count them on one hand. So I think psychologically for the public, when they're always hearing positive reporting, positive projects, then there's no negative association with geothermal projects. The role of the first projects being from municipalities shouldn't be underestimated, because they have to have a very transparent approach to the projects. They have to go through a number of public consultations. They need to really be in touch with the local communities to make sure that they understand the projects on a economic and a technical level. So I think this approach can also be taken away from many operators. Also in the UK, the recent example of the United Downs project, there was a real extensive public consultation which went on there, and it's a very good example of how it can be done well to make sure that the public are well informed. So that goes together with then good PR work and education of the people. The example out from Munich, when you have these big vibration seismic trucks running through the city, so through the city center, you can see the tram alongside it. You need to be telling the people why. They need to understand why. They need to understand what it means. They need to understand if they have any concerns, if they have any problems, who they should speak to. 100% transparency of these kind of things is essential. And there are sometimes cases maybe for projects where the public pushback is too high. The question is how much do you want to, and can you fight against it? If the public aren't ready to accept it, then maybe it isn't the right fit. And that goes together with the subject of seismicity. So the projects the operation of the project is causing some kind of seismicity. So the Bavaria region, we've been very lucky. It's not so seismically active or sensitive. There's obviously recorded events, but they're rarely felt. The recent largest one being one of the largest ones being Poing in 2016, and following that there was a lot of work done to understand why it happened. And it really means that through this understanding, the approach is really to mitigate it. So the design, the engineering done for the projects will be done in such a way that we will look to avoid any kind of constellation which mechanically activates any of the formation at depth. There's a requirement, a regulatory requirement to monitor prior to drilling and then during operation. So seismic monitoring stations are compulsory, and then managing during that. So we're having full understanding of what's going on in the subsurface, so simulations, models, geomechanical models, and then being able to change the operational conditions, so the injection rate or the injection temperature in response should anything happen. So a strong developer and planner partnership delivers, in our experience, a lot of good successes because the lessons learned can be taken from project to project. So this slide's a little bit dated now, but it across the x-axis we have then from 2008 to 2016, and the y is a normalized drilling time, so number of days to drill 1,000 meters. And the dots are all wells in and around Munich. And we can see that the general trend is a reduction in the total number of days to drill 1,000 meters. And all of these projects were on a day rate contract. That means if you require less days to drill, your project costs less. So it meant that we saw a reduction in the cost per meter. So at the higher end, 1,500 euros a meter, going down to somewhere around 1,100 euros a meter. So the reason for this is planning, is lessons learned, understanding the formation, being able to put the right drilling methods in place for the different formations and making decisions proactively and not reactively. Also an improvement or the use of different drilling technology, really embracing the oil and gas drilling standard, using rotary steerable systems to be able to accurately reach the targets that we've set within the formations. And the example of the Unterföhring 4 well projects, so two doublets. The first two demonstrating slower drilling times, then higher costs, but the lessons learned there being able to be applied in the subsequent wells and dramatically reducing that. So making sure that these lessons learned don't go lost by changing planner between projects or wells, or that the information isn't available for the next people to plan, really be able to build on that. We think that this curve should level off as we reach the limits of the technologies which we use as standard for deep geothermal projects, so the oil and gas standards. The introduction of new technologies will definitely be able to improve this more. So as mentioned a number of times, the oil and gas exploration production workflow is essentially the backbone now for what we do within the geothermal sector. So the technology back early 2000s, it all looked quite simple. Often seismic profiles, well, 2D seismic profiles within some kind of GIS software. But today, now with 3D seismic surveys, we're able to model, target and simulate the reservoirs in 3 dimensions. So meaning that the Petrel Eclipse landmark for reservoir engineering, drilling engineering, the standards of oil and gas are now the standards for geothermal, as well as the technology, the rotary steerable systems, now there's been a number of projects, and also one of our projects within Munich where we have a multilateral completion, so a additional branch to an existing well. Be able to mention that in the next couple of slides. Health and safety always plays a significant role, but really that the health and safety on site during drilling is the same as oil and gas. There's no difference. It's not just drilling water wells. It's not just simply drilling down. It's highly complicated, deep drilling, and there should be no difference from the oil and gas standard. So the human resources, this transition that we see now, the industry crossover, there are a number of workshops looking to find common ground between the oil and gas and the geothermal industries. And we see now there's a lot of large oil and gas operators have got involved in projects, most recently Rotterdam, where Shell are involved. And this can only be a good thing. Not only does it bring a little bit more of a financial security, but it also brings a more of a portfolio approach where it's not just 2 wells, it's looking at the whole region, which means the projects are upscaling. It's not just 2-4 wells for a small community. What we'll see in the next couple of slides, it's multiple wells for a city.
Hey, Neil, sorry to interrupt you, but
yeah,
there's a lot of questions in the chat. I'm just wondering if we could finish up maybe in a few minutes and let the people ask you a few, because it's just a worry of time.
Yeah, no problem. I'll skip forward a few slides just to show.
It is really great, but I'm just aware of the time. Thanks.
That's not a problem. Not a problem at all. I'll skip forward. So this slide just mentioning the importance of centrally held information, whether it's in the Netherlands or the French databases. But I will just skip forward a number of slides so we can just show the examples of what's been done in Munich at the moment. So the city of Munich, the utilities company here on the right hand side, we have the blue areas of the district heating networks, and their goal is by 2050 to supply all the district heating networks with heat from geothermal projects. To enable that, there was a significant 3D seismic survey. So this kind of pink-orange area was where the vibro trucks were driving around, undertaking the seismic survey. And on the basis of that, there was a theoretical approach initially that 50 wells required to be able to produce the 400 megawatts thermal required for all the district heating networks within Munich. Theoretically, it looks like that. In reality, or not in reality, but I guess a little bit more. The next step, planning, is a little bit more accurately. There aren't enough well sites, so it means more wells from one well site, which led us on to Schärflandstraße, which was just completed at the end of last year. Middle of last year, which is located in Sendling, one of the most densely populated parts of Munich. And there we drilled 6 wells from one well site, going to a depth of about 3,000 meter vertical depth. And we also had one multilateral completion. So that's the one, the 2A, which is this one here. This is the multilateral branch, which was planned to go a little bit further, but actually after about 300 meters, we encountered quite a significant cavern or karst formation or karst feature, and we were unable to drill any further. However, the project, or the pilot project, proved that the extra cost of planning a multilateral branch was economically positive, and over the course of over the length of the lifespan of the project, it will be paid back significantly. So yeah, the total project producing then 50 megawatts thermal, producing a temperature of around and over 100 degrees Celsius, with an average production rate over 100 liters a second. And when it all goes well, then during testing, then we hopefully see these kind of scenes where a lot of steam. Steam is good. Steam means hot. And then I guess just summarizing then we've identified is that there are issues. The costs will always be an issue. The slow return of investment for heat projects will always be an issue, but there are a lot of important drivers. And I think the political change, the climate targets are some of the biggest drivers. The motivated people within the industry, subsidies need to support it to try and make it geothermal competitive with the gas price, for example. And the solutions being open source, I think, is very important. I think having information available to be able to undertake a feasibility study of a project based on open source information before data is purchased. Research innovation can only drive down costs long term. Centralized risk mitigation, so a feasibility insurance or risk insurance as well is very important. And if the government's willing to carry that, then I think it takes the risk away, a lot of the risk away from the operators and makes them more inclined to do these projects. And I guess the last point is then the portfolio approach. So as we see there for the city of Munich, that it's not just 2 wells, it's as many wells that the reservoir can feasibly and sustainably handle. So yeah, a lot of information. I guess I could have gone for a lot longer there, but thank everyone for their attention. My email address is there if anyone wants to follow up any questions or discussions over the next weeks. But thank you very much for your attention.